So this is part 3A of the shells method series. We will find the height and radius of the rectangular slab that we talked about in part 2, but specifically when rotating around the y-axis. So I'm going to assume that you've already watched part 1 and that you've already watched part 2 of the series, and so we'll pick up from there. So in part 2, we wanted to find the volume of the cylindrical shell. And in the last video, we came down to this formula for the volume of the shell. And we only needed to find the height and the radius. And so going back to this rectangular slab, our width we found in part 2 is 2 pi r, and our height is still unknown. We haven't talked about it, but we did see that it was related to the height of the rectangular cross-section that we take. So we're first going to get our formula for the height. And let's put this height back on our graph so it's easier to see. And we can get rid of all the extras. And now we can see better. And here we can see that the height of that blue line, the length of that blue line, is actually the length from the x-axis up to the graph, which we can just call f of x. And so the height is f of x. So now we have the height for our rectangle. And now we can talk about the width of the rectangle. So we just need to find the radius to find the width of the rectangle because we already know 2 pi is just a number. So moving backwards to part 2, where we found the width to be 2 pi r, that was part 2 of the series. And we just need to find r. So here is our width of the rectangle put onto our cylinder. And let's just go ahead and put that cylinder back on our graph because then that's easier to come up with a formula. And remove all the extras so that we can see better. It almost looks like the radius goes to that green curve, but let's zoom in to actually check that. So R actually, if you look at it zoomed in, it comes out to the rectangle, not the curve. And it also stays at that distance because it is the radius of the cylinder. So you can see that that distance is always going to be the same no matter where it is on that cylinder. So what is this distance? I think this is less confusing when we actually put that radius out to the cross section, and it's easier to come up with the formula. So this distance is just associated with the x distance where the rectangle is drawn. So where we draw our rectangular cross section, that distance from the y-axis is going to be that distance of r. So we can just say r is equal to x. And we just use general x because the distance to these rectangles is always different. Remember, we build our rectangles left to right. And so that x value is going to always change. And then we integrate over x. And that integration will account for all of those different x values on every interval. So you may need to pause and just kind of think about that with your understanding of the definite integral. So now we have that our width is going to be 2 pi times x. And we had our height is f of x. And so our volume will be the width times the height, which is 2 pi x times f of x delta. And if we go back to part 1 of this series where we asked the big question, which is what is the volume of the 3D shape? We really came down to the question is what do we put in that integral? We know it's the volume of the cross section. And we know that if we just add up the volumes of all those little cylinders, all those cross sections, and take the number of cylinders, the number of intervals to infinity, we will get that definite integral of the cross-sectional volumes. And now we know that that is going to be this 2 pi x times f of x dx. And so we have our formula when rotated around the y-axis. And just, one quick note, we had this graph, but what if we had this other graph below it? And our region became this area right here. How would things change? So let's take a cross section and rotate it around to get our cylinder. And throw in our radius and our height. And our radius is still the same. It doesn't really change. Um, it'll still be the y-axis to, the rectangle, which is x. So our width is still 2 pi x. But our height is different because the rectangle no longer goes from the x-axis up. And let's go ahead and remove everything so that we get a better look. And we can see that that height is going from the top curve uh, down, so minus the bottom curve. And that will be, the height of our blue line. So if we call the top curve f of x and we call the bottom curve g of x, then our height is just going to be f of x minus g of x. And so now our volume, instead of just being f of x, we get an f of x minus g of x in this integral. Okay, so thanks for watching. You can join me in part 3B of the series to see the shells method when we rotate around the x-axis. All right, thanks. See you there. Bye.